Good morning, everyone. For the previous course, we have been discussing about the viscous flow in pipes topic, water flowing in a culvert, oil in a pipeline, blood in an artery, all flows completely enclosed by a solid boundary. And it was a world governed by pressure, friction factors, and Moody charts. Today we are breaking free. We are opening up the conduit and letting the fluid breathe. We are stepping into the world of open channel flows. Now take a look at this opening photo, that powerful image of a hydraulic jump, water suddenly surging upwards in a foaming mess, something that cannot happen in a pipe. Why? Because in an open channel, the fluid has a free surface. It's exposed to the atmosphere. Now think about it, that the Colorado River carving its way through the Grand Canyon, the water rushing down the gutters on your street after a rainstorm, the flow in an irrigation canal feeding a farm, even the shoot of the water right at an amusement park. All of these examples of open channel flow, they are all around us. And the main driver here is not a pump, it's a gravity. The fluid has own weight is what pulls it downhill. So, as we dive into this new world, we need a new way to describe it. The classifications we use for pipe flow, that is laminar, turbulent, steady, or unsteady, are still here. But the free surface adds a whole new layer of complexity and fascinating behavior. Our goal for the next half hour is to map out these journal characteristics and set the stage for understanding the waves on that free surface. Now, just like in pi flow, the first way was we classify the open channel flow is by looking at how it changes with the time. We ask that does the depth of the water, which we denote by the letter Y over here, can change with the time at a given location? If you stand on the bank of the river and the water level is constant, the flow is steady. But if a surge comes through and the water level rises and falls, it's unsteady. Now, here is a cool thought. Some unsteady flows can become steady just by changing your point of view. If you imagine a tidal bore, the wall of the water that moves up a river with a incoming tide, to you standing on the bank, the water level suddenly jumps up and then keeps flowing. It's unsteady. But if you were in a boat moving with that wave at a same speed, the wave profile in front of you would appear stationary. From your moving perspective, the flow would look steady. So in this topic, we are going to stick to the simpler case and focus on the steady flow. The second major classification is about how the depth changes along the channel, the distance x. Now, if you walk along the bank and the depth y remains perfectly constant, we call that uniform flow. In the diagram displayed over here, dy of d of x, if it is equal to 0, this is the ideal case, like the perfectly straight man-made canal. But for most natural channels are not this perfect. If the depth does change with the distance, meaning that dy over d of x is not equal to 0, we call it the non-uniform or the varied flow. Now, this varied flow comes in two different distinct flavors. Now, think of a river going over a large boulder. Right at the boulder, the water surface might drop and roil violently in a short distance. That's rapidly varying flow, or we abbreviate it as RVF, rapidly varied flow. So dy over d of x is on the order of 1. It's complex, turbulent, and full of energy. But on a longer stretch of the same river, the depth might change very, very slowly as the river valley widens or narrows. That is the gradually varying flow, or we abbreviate it as GVF. Here, dy over d of x is much, much less than 1. The change is so gradual, that you can barely see it from one spot to the next. The behavior of these flows, either it is RVF, rapidly varied flow, or a gradually varying flow, GVF, is completely different because the balance of the forces in terms of gravity, pressure, friction, and inertia is different. So we will touch on the GVF later on, but for now, just remember that the rate of the change of the depth is the key descriptor. Now, let's talk about the viscosity. You all remember that the Reynolds number from our viscous pipe course earlier. Well, open channel flow has its own version. It's given by the relationship Reynolds number is equal to rho v r subscript h divided by the nu, which is the dynamic viscosity over here. But you will notice a term as the r subscript h, which is called as a hydraulic radius over here. Don't let the name scare you. It's a simple geometric concept. It's defined as the cross-sectional area of the flow A divided by the wetted parameter P. Now, the wetted parameter is just the length of the channel boundary that is actually in contact with the water. The part of the boundary that is just air does not count. So R subscript H, which is the hydraulic radius, equals to area over perimeter. For the Reynolds number, if it is less than 500 in number, we say that the flow is laminar. But if it is greater than 12,500, we say it is turbulent. And in between this range, that is in between 500 to 12,500, the flow is transitional. Now, what do you think? Is most open channel flow laminar or turbulent? Let us do a quick example from the text. Imagine a large river like the Mississippi. It might have a velocity of 1 feet per second and a hydraulic radius of 10 feet. Plugging in the numbers gives the Reynolds number of about 7 lakh 10,000. It's highly turbulent. Now imagine a thin sheet of the water flowing down the your driveway after you wash your car. It might be moving at 0.25 feet per second and have a depth of just zero point zero 0.02 feet, which is roughly its hydraulic radius. Its Reynolds number is about 355 in a number that we classify the flow as laminar. Now you can see that the smooth glassy surface over here. So what's the summary? In most practical large-scale applications, rivers, canals, flood control channels, the flow is mostly turbulent. The laminar flow is reserved for very thin sheets or very viscous fluids. It is important because the empirical equations we will use, like the Manning equation, are based on the physics of turbulent flow. All right, we have talked about the depth variation and viscosity over up till now. But the presence of a free surface gives us a new and arguably the most important dimensionless number in the open channel hydraulics. So, which is the Froude number, often abbreviated as the FR. So, and it's related by the relationship over here as V over under root GL, where L was the characteristic length up till now, but for our purpose in which we are discussing the open channel flows, this length L is being replaced by the flow depth Y. So we can write this particular equation Froude number equals to V over under root Gy. Now, what does it represent physically? Think of the term that is under root Gy as the speed of a very small simple wave on the water surface. It's the speed at which the ripple will travel. So the Froude number is the ratio of the flow velocity to the wave speed. This particular ratio is what determines the entire personality of the flow. It also tells us whether the fluid is flowing faster or slower than information in form of the waves can travel on its surface. So let us break it down into three regimes, which are illustrated beautifully by the figure as in this particular slide. So number one is the subcritical flow, second is the critical flow, and third is the supercritical flow. These are the three regimes classified by the Froude number values, and I would be explaining them one by one. Now, if the Froude number is less than 1, it is called as a subcritical flow. Here, the flow velocity is less than the wave speed. The wave can travel upstream. The Imagine if you are throwing a pebble into a slow-moving stream, the ripples spread in all the directions, including the upstream. This flow is often called tranquil or slow and deep. In this regime, the downstream conditions can influence what's happening upstream. There is, in engineering terms, we call it as the hydraulic communication upstream. So, second one is the critical flow if the Froude number is equal to 1. This is special. Knife edge case where the flow velocity equals the wave speed. A wave that is trying to go upstream would appear to stand still now. It's the dividing line between the two very different worlds. The third one is the supercritical flow defined when the Froude number is greater than 1. Now, the flow is racing faster than the wave speed. If you throw that same pebble into a shallow, fast moving stream, what happens now? The ripples can't fight the current. They are all swept downstream. No information can travel upstream. The flow is rapid, shallow, and fast. So the upstream locations have no idea what's happening downstream because the waves cannot get to them. Now, on this particular slide, I have shown you three simple sketches that one with the circular ripples centered on the rock, showing upstream propagation, which is hereby is represented as a subcritical region. The second one is the one with the rock and all the ripples swept into a V-shape downstream, which is a supercritical region. The third and the last one is the critical region, in which one where the ripple appears to be stationary right on at the rock. So this is the critical case. This difference between the subcritical and the supercritical flow is not just theoretical. It dictates the shape of the water surface over the obstacles, the formation of the waves, and the very existence of the phenomena like the hydraulic jumps you saw in the opening photo of this particular topic. Now let us bring this to life with a real example which deals with the Rock River. They have given us a relationship between the river's velocity v and its depth y from the experimental data. Related by this particular relationship, v is equal to 5 times y raised to the power 2 by 3, with v in feet per second and y is in feet. So the question is, for what range of the water depth will a surface wave be able to travel upstream? Now think back, we have already studied it. For a wave to travel upstream, the wave speed must be greater than the river's velocity. In other words, the flow must be subcritical. We need C to be greater than the velocity V. C must be greater than the velocity V, where C is equal to under root gy. So we set up the inequality and write this particular equation as under root gy must be greater than 5 times y raised to the power 2 by 3. So let's plug in the numbers and we want the depth y that satisfies this, so we can solve for this critical depth where under root gy equals to 5 multiplied by y raised to the power 2 by 3. So by squaring and by rearranging and by cubing on both sides, we get the final critical depth as yc equals to 2.14 feet over here. Now, what does this mean? If the river depth is less than 2.14 feet, the flow velocity is high enough that the Froude number is greater than 1. So the flow will be supercritical over here. A wave cannot travel upstream. But if the river depth is greater than 2.14 feet, the flow is slower and the Froude number is less than 1 and the flow is subcritical. A wave can travel upstream over here. So the answer to the problem is that a surface wave can travel upstream for any water depth greater than 2.14 feet. See how that works. We use the fundamental concept of the Froude number and the wave speed to determine a real physical outcome. This simple parameter dictates whether a rock thrown in the river will send ripples upstream to alert you, or whether they will all be washed away anyway by the downstream in the downstream. So this concept is huge. It determines the fundamental behavior of the flow. Um, we have two fascinating examples over here to further illustrate it. The bump on the bottom. Imagine a submerged log in a river, in a deep, slow, subcritical river that bumps in the bottom will cause the water surface to dip downwards as the water speeds up to go over it. But in the shallow, fast, supercritical river, that same bump will cause the water surface to rise, piling up against the obstacle, the exact opposite direction. Now, the second one is the hydraulic jump. This violent step up in depth from shallow to deep only occurs when you try to go from a supercritical flow to a subcritical flow. The flow is going so fast that the Froude number is greater than 1 over here, that it's outturned its own ability to smoothly transition. So it has to break and jump to a new, deeper state to match the downstream conditions. It is the only way to reconcile the two flow regimes. And here is an amazing analogy for the engineering minded among you. This behavior, subcritical and supercritical, is a direct analog to subsonic and supersonic flow in gas dynamics. In compressible flow, the key parameter is the Mach number, which is the ratio of the flow velocity to the speed of the sound. But in the open channel flows, it's the Froude number, which is the ratio of the flow velocity to the wave speed. Many of the equations and concepts we use in one field have a direct counterpart in the another. A hydraulic jump is the analog of the shock wave in the supersonic flow. It's the same fundamental physics, just in a different medium. So we have covered a lot of the ground. We have seen that open channel flow is classified by how its depth changes in time, whether it is steady or unsteady, and whether it change in the space also, like uniform or varied. We have also introduced the hydraulic radius and confirmed that most practical flows are turbulent in nature. But the star of the show is the Froude number. Froude number is represented as V over under root GY, is the Rosetta Stone of open channel flows. It tells us if a flow is subcritical, critical, or supercritical. Like if the Froude number is less than 1, a deep, slow, tranquil world where waves can travel upstream. But if it is critical, we can say that the Froude number here is equal to 1. That's the razor's edge. But if the Froude number is greater than 1, we say this as the supercritical flow, a shallow, fast, rapid world where everything is swept downstream. So all of these classifications, subcritical, critical, and supercritical, hinge on a behavior of the surface waves. Now, what is the wave? How fast does it travel? Does its speed depend on its size? The answer to these questions form the foundation for everything else. And that's precisely where we are headed next. In the next section, we are going to dive deeper into the next topic, which is the surface waves. We will derive the equation for the wave speed, c is equal to under root gy, and that we have been using up till now, and we will see how wave speed changes for tiny ripples versus giant tsunamis. We will build the very language that the Froude number speaks. For now, I want you to look at the world around you with new eyes. Next time you see a stream, a gutter, or even water from a faucet hitting your sink, ask yourself, is this flow subcritical or supercritical? Could a wave travel upstream, or is everything rushing downstream? That's the power of what you have learned today in this particular lecture. See you next time in next section. Thank you.